Hello, in this video I will be helping you to solve a problem, answer a question in AP Physics C Mechanics, the free response question part, section 2. This is the question 1 in the real past paper last year 2022. We are given here an object, a block of mass m can move smoothly, not really smoothly, on a table. Of course, there is friction on the table, and the coefficient of the kinetic friction is mu k. This object is pulled by a motor here, attached to the object by a string. The mass of the string is very low. The mass of the pulley here is also very low, so that we can ignore the loss of energy to rotate this pulley, and we don't need to involve the moment of inertia and the torque acting, how this pulley will affect the motion. So basically we just use the Suvat, the big 5 equation for the mechanic part to solve this problem. In addition, the friction of the string between the string and the pulley here is also very low. Those things are mentioned in the statement of the problem. Secondly, it is very important to note that the tension of the string, the tension provided by the pull of the motor when it rotates, is a constant. This tension is constant. It is called Ft. The object starts moving from the position x equal L here, and the position here on the left edge of the table is defined at the 0 position, the origin of the coordinate system. We know these things: the mass m of the object, the height, initial height, h here, when the object at the position L, also a constant, the given value. The coefficient of the between the object and the table is constant, and the last thing that we are given is L, which is the initial position. Okay, now moving on to the questions. The question A, on the dot below, represent the block, draw and label the forces that act on the block when the block is at the position x equal L. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Okay, I will draw the free body diagram on this dot later. Now I like to explain it and draw it here directly on the diagram so that it helps you understand this problem easier. There are 4 forces acting on this object. Of course, the first thing is gravity, the pull of the earth acting on the object W, or we can write it as the mass of the object multiplied with the gravitational constant G. Secondly, the tension Ft, that the string pull the object, T for the tension. This tension is given by the problem. It is a constant. Okay. The third force is the normal force, the supporting force of the table, the normal force. Normally, if an object is on a horizontal surface with no other forces pulling it, the normal force here is equal to the weight acting on the object, equal to the weight of the object W. Okay, but in this case, the normal force is not equal to weight, but less than that, because the sum of the upward component of the tension, which is this component, the tension here has 2 components. We can analyze, we can resolve the tension force into the 2 components, Fty, the vertical component, and Ftx, the horizontal component. Ftx horizontal component. Okay, therefore this upward component Fty provide a lifting force on the object, and this is Fn, normal force. Okay, the point is the sum of those 2 upward forces, which is the upward component of the tension Fty and the normal force Fn, it must be equal to the weight W there. So this is the most important thing when we draw a free body diagram. And lastly, the last force is the friction between the table and the object. the friction here, I can draw it right here, must be less than the horizontal component ftx to the left. Okay, so this last thing is the friction Fr. Now, to draw this free body diagram correctly, the first force that we should draw is the tension, because it is a constant. Okay, Ft. The second thing is Fn. I do not draw the wave first because I will draw it later, so that the sum of the vertical component Fty and the normal force Fn will be equal to the weight. So that I draw the weight later, thirdly. Okay, so this is the weight W. And lastly, the friction Fr. Friction Fr. The friction here should be lower than or greatest equal, its greatest value is equal to the horizontal component of the tension. It should be less than the Ftx, so that the object, the block, accelerate due to the pull of the motor, the string. Okay, so this is the answer to the question A. Moving on to question B. Derive an expression for the angle that the string makes with the horizontal as a function of x. Okay, derive expression for the angle. As you can see directly on the diagram here, the angle theta is here, and we have this triangle. So from that triangle, we can see that the sine of that angle is the opposite, which is h here, opposite over the hypotenuse. Hypotenuse is this length of the triangle. Okay, so that hypotenuse, according to Pythagorean theorem, is the sum of the square of the two other sides, which is the horizontal side here, which is x square. Okay, and add it with the other side square, which is h square. So this is the side of the angle. Okay, and therefore we can derive the function for x. We have that the sine of that angle theta is opposite h over the hypotenuse, which is x square plus h square, and therefore the angle is the inverse function of this value, h over square root of x square plus h square. This is the answer. But there is a second way to write the expression for the angle. That is, we can use the tan of the angle. Okay, tan of this angle theta will be equal to the opposite of adjacent, which is h over x, and therefore theta can also be represented as the inverse tan of h over x. Let's move on to question C1. We ask now to derive a expression for the normal force Fn exerted on the block by the table as a function of the block's position x. Expression for the normal force Fn. Okay, we will start from the first equation that I told you in the question A, the most important equation. The vertical component of the tension Fty plus the normal force Fn equal to the weight mg. We need to derive Fn. Okay, so Fn will be equal to the weight mg minus this vertical component Fty, and that Fty is determined by Ft multiplied with sine of the angle theta. And lastly, we will write the last expression. Sine theta here, we also determine it in this expression above, question B here. So that's sine theta is equal to h over the square root x square plus h square. Okay, and Ft here is a constant. So this is our final answer. The next thing, derive an expression for the magnitude of the net force, net horizontal force F net exerted on the block as the function of the position x. The question here is the net force, but only the horizontal component, not the total net force, not the sum of all the four forces acting on this object, only a horizontal component, which means the component of the tension in the x direction going to the left, and we need to subtract it with the frictional force resisting, opposing the motion of the object going to the right. Okay, This is the net horizontal component fx net. ftx will be equal to ft, the tension, multiplied with cosine of the angle. Okay, and the friction, as you already know, that the frictional force is determined by the coefficient of friction multiplied with the normal force Fn. And we will plug the expression of Fn here into this expression to find the frictional force. Okay, so that frictional force is the coefficient of friction mu k multiplied with the normal force, which is mg, minus tension multiplied with the height divided by square root of x squared plus h squared. Okay, so this is the expression for the horizontal net force. This is the answer. The next thing, question D, write down but do not solve an integral expression that could be used to solve for the work done by the string on the block as the block moves from x equal L to x equal 0. Expression to solve for the work done by the string. We can see that when the object here slides from the right to the left, the angle that the string makes with the vertical direction changes. This angle theta changes, getting bigger and bigger. Okay, for example, when the object moves to the new position here, the string attached to it will make an angle like this. Theta, the angle theta now here, will be greater than before. Okay, so that angle changes, and therefore the two components, ftx horizontal component and fty vertical component, those two components will change. Definitely the work done by that force, the tension, is not expressed by an easy and simple expression as force multiplied with the displacement d times cosine theta in the definition of the work. It is not simply determined by this expression, okay? Because the force, the tension, changes with the position x. So that work must be determined by the integral of the tension ft, okay? And we need to multiply with the infinitesimal dx, a extremely small displacement of the object on the table, extremely small displacement such as 1 centimeter or even lower, like half centimeter. Okay, and we need to also multiply the cosine of the angle, not theta. I will use another angle, angle pi, which is the angle between that tension ft and the infinitesimal displacement dx. This angle, that is actually theta, right? Yeah, times cosine theta. Sorry, it's not pi, it is theta times cosine theta from the definition of the displacement. Okay, and one more thing which is crucial, very important, but many students will forget, that we are given that the coordinate system is like this, meaning the positive direction x is to the right and positive direction y is upward, and therefore dx here will be negative, and therefore for this work, this is definitely a positive work, providing the energy to move the block, and therefore if we do not put a negative sign here into this integral, the calculation will be a negative value, and therefore to make it positive we have to put a negative sign in front of the integral, okay, cosine theta. And similarly we can express the cosine in terms of x and h. We have x here, we have x here, and this is the angle. So cosine of this angle is the cosine here. Okay, that cosine is adjacent x over hypotenuse, which is the square root of x squared plus x squared. And I will put the infinitesimal dx here, and ft, which is a constant here, and a negative sign in front of it, and integral. Okay, this is the expression, the final expression, the final answer of this question. Okay, so it's very important for the negative sign here and the correct expression for the cosine of x. ft here, remember, it is a constant. The last one, question E. Does the string do more or less or the same amount work on the block as the block moves from x equal L to x equal L over 2 compare to when the block moves from x equal L over 2 to x equals 0. Let's look at the diagram one more time, the last time, huh? Okay, when x moves from L to L over 2, L over 2 is like here, meaning the displacement is in this region, and compare the work done by the string in this region with the work done in the other half region on the left here. How do you think? What do you think? In which region the tension will do greater force? We can see that the angle increases. The angle theta increases when the object moves to the left, and therefore cosine of a increasing angle, this angle increasing from not 0. For example, this is 10 degree, just example, okay? From 10 degree going up to here almost 90 degree. I can say like 89 degree. So the angle increasing, and therefore the cosine of that angle will decrease. We know that in the first quadrant, the cosine function is a decreasing function, okay? And therefore the cosine in this expression, the cosine here in this expression will decrease. This thing, you can use a graphing calculator also to plot the graph of this thing, and the graph will look like this. This is the y value, and this is the x value. The graph will decrease from a asymptote like this and go like this. If we only consider the positive part, it will decrease like this, and therefore going to 0 when the angle approaches 0 degree. Okay, and therefore the work for the second part moving from L over 2 to 0 will be less, and the work done for the first part moving from L to L over 2 will be greater. Okay, so the answer we would choose that more. We choose this one. More work when the block moves from x equal L to x over L over 2. Okay, and finally we need to justify the answer. Thank you very much for spending your time and watching this video until this moment. Please leave a comment below if you like the video or you have any question, and if you don't mind, please help me by clicking the like button or subscribe the channel. Thank you very much, and hope to see you again in the next video.